before we start 1.1, let's actually talk about what chapter 1 is all about. And I'm just on page 2 in your textbook. So chapter 1 is going to cover everything that we're going to cover all year long. It's going to kind of give you an introduction to the 4 main concepts of calculus, which are limits. We've already dealt with limits a little bit in pre-calculus. We basically said, as x is approaching some input, y is going to approach some output, right? So as I approach c here, this function is approaching some output, which is the limit. Even though it's not defined at that value of c, right? We still can say, well, there's a limit because both the left and the right of this graph is approaching the same output. Derivatives are very important. They're basically instantaneous rates of change. Now, we've talked a lot about average rates of change, which is basically just slope. So instantaneous rate of change is where there's no time change. Okay, we'll talk more about that. And then 2 different types of integrals, the definite integral and the indefinite integral. And looking at this graph, that's represented here as the shaded region, which is truly just an area. Okay, so we're just dealing with areas, and we'll use areas of rectangles, trapezoids, and then we'll use calculus to get a better approximation of this area here, or an exact amount. There are 4 ways that we'll talk about these concepts, and we've already done this. One of them is graphically, right? So using an actual graph. Numerically means using an actual table. Algebraically means using some kind of algorithm. This is an algorithm here for an average rate of change or slope. And verbally means using words, writing about it. All right, so moving on to 1.1, our assignment here is 1.1, the concept of instantaneous rate. And your essential question is, how do you estimate the instantaneous rate of change, and I used a delta for change, at a given point in time? And I'm just going to remind you about average rate of change first, and then we'll get into instantaneous rate of change and kind of what the difference is. So you've dealt with average rate of change quite a bit. So average rate of change. And that's really just slope, right? Okay, so we have approximated the average rate of change using slope, which is like rise over run, or the change in y, which is your vertical axis, over the change in x, which is your horizontal axis, or actually using the coordinates of 2 points that we're trying to find the rate of change between. So saying y2 minus y1 over x2 minus x1. So that would kind of be your algorithm. Okay, so let's say, for example, I give you a graph. We'll do a pretty simple graph here. We'll have a vertical axis and a horizontal axis. We'll make this a displacement graph. So movement. And we'll say some object moves a certain amount of feet. So that's like the distance. Over some amount of time. So how about over some amount of seconds? So that's like the time. I'm just going to use a really simple one. So we'll do a line, like you've been seeing since you were in Algebra 1. And how about on the feet axis? You know what, I'll label that y and I'll label this x. I don't know. Let's do d and t instead. How about that? Right, for distance and time. How about that? Okay, so on the vertical axis or the distance or the feet axis, I'm going to go by units of 5. So 5 feet, 10 feet, 15 feet. And on the t, the x, the horizontal axis, I'm going to go by units of 1. So we'll go 1 second, let's go 2 seconds, and then 3 seconds. Okay, and I'm going to find the average rate of change between this first point here, which is at 1 second, we're at 5 feet, and the third point here, which is at 3 seconds, we're at 15 feet. Well, to find the average rate of change between these 2 points, I basically just want my rise over my run, right? Or the change in that vertical axis over the change in that horizontal axis, right? So the change in y over the change in x, or in this situation, change in d over the change in t. All right, so my average rate of change here, okay, well, looking at my y-axis, I'm going to go from 15 to 5, so that's really 15 minus 5. And then looking at the horizontal axis here, I'm going to go from 3 to 1, so 3 minus 1. So we get 10 over 2. Oh, you know what? I should use units. Sorry, I got distracted because there's a lot of screaming happening outside. Crying. So it's 15 minus 5 feet. And then it's 3 minus 1 seconds. So it's feet per second. So it's going to be 10 over 2 feet per second, or 5 feet per second. Now, when I find the rate of change of displacement, well, I get this unit of feet per second. Well, what idea is that? Well, that's actually velocity, right? So this right here, when we found the average rate of change of displacement of movement, we got a velocity, right? Like a speed. Okay, so that's the average rate of change. Let's see, do I have a highlighter here? That was all average rate of change. You're very familiar with that. You're familiar with slope. So now let's relate that to instantaneous rate of change. Okay, well, what does instant mean? I guess that's what we really need to think about. What does it mean for something to happen in an instant? Well, an instant means 0 seconds or 0 time, right? Time hasn't passed at all. So an instant equals 0 time, right? So that means that there's no change in time. So back to this, it would just be like if I was trying to figure out the instantaneous rate of change at 1 second, right? There'd be no change in time. I'd have nothing to compare it with, right? So that's when basically you're trying to figure out, you're dividing how far you've gone by 0 seconds. Well, that's impossible. How the heck do we do that? Okay, so if we're thinking about this, we can think of it, if we use the slope formula, that's where you're going to have your slope is going to equal, well, some change in y over 0, right? And this is undefined. So this is where calculus comes in. Okay, we're going to be able to use the derivative to find this. Okay, so that's where the derivative comes in. It's this calculus that allows us to find this instantaneous rate of change, because using the slope formula is not going to help us. Now, we can get really, really close to finding the derivative using our slope formula, right? Using this average rate of change. Okay, but we're going to be able to estimate it. We're not actually going to be able to find the actual instantaneous rate of change, which is why our essential question said, how do you estimate the instantaneous rate of change? So in this lesson today, we're going to use the average rate of change to help us estimate the instantaneous rate of change. Okay, so we're going to try and get like really, really small amounts of changes in time. So you can get as close to an instant as possible by estimating the rate numerically. Okay, so we can get as close to an instant as possible by estimating the rate numerically. So we'll use some tables here, tables of values. And then by finding the limit of the average rates and by finding the limit of the average rates as the time interval gets close to 0. So we'll get that denominator as close to 0 as we can. And we'll kind of take the limit, like what is it approaching as our time interval gets really close to 0. And that's how we're going to estimate it. Okay, we're not going to get the exact instantaneous rate of change, but we can definitely sit here and explore it using our algebra. Okay, so I gave you guys a handout. The exploration 1-1 instantaneous rate of change of a function. Okay, and so we're going to go ahead and explore this idea of the instantaneous rate of change by approximating or by estimating it using average rates of change. All right, so the diagram shows a door with an automatic closer. At time t equals 0, someone pushes the door. It swings open, it slows down, it stops, it starts closing, then it slams shut at time t equals 7 seconds. As the door is in motion, the number of degrees d it is from the closed position depends on time t, on t. Okay, so again, I'm going to kind of make a big deal. I want you guys really focusing on the units. So when you're graphing, make sure that you label those axes. When you're calculating slopes or rates of change, make sure that you're using your units in there as well. Okay. So I'm drawing my 2 axes. The vertical one is d for degrees. You can even write that in. And the horizontal one is t for time, which is in seconds. So t, and again, I'll write in the fact that it's in seconds. Okay, so at time t equals 0, someone pushes the door, so it starts to open at time t equals 0. It swings open, right? So it starts to swing real fast, but then it starts to slow down. So the rate's going to be a little bit less, so it's not going to be as steep of a line or as steep of a curve. Okay, then it stops. Okay, so that means that the rate is 0, and horizontal lines have rates of change that are 0, so it's going to become kind of horizontal. It's going to start closing, and then it's going to slam shut, so it's going to go quick again. Okay, so I would imagine if we start at time 0 here, and we're ending at 7 seconds here, right? So it's going to be at 0 degrees at 0 seconds, 0 degrees at 7 seconds. Somewhere in between there, it's going to flatten out. So it's going to start off fast, start to flatten out. It's going to stop. So it's going to be like flat, horizontal. Then it's going to start to shut again, and then it's going to slam. Okay, so it gets back to being. So something like that. That's probably not exact, but something like that I think would be reasonable. Now, they didn't give us any degrees, so I can't really label the d-axis. Now, suppose that d is given by this equation. Now I can get more specific. So they've given us this equation. Plot this graph on your grapher and sketch the results here. All right, so get out your grapher. Okay, we're probably going to want to deal with our window a little bit here. So let's see, my x-axis or my horizontal axis needs to go from 0 to 7. But my degrees, like think about opening a door, right? Or doors don't usually open 360 degrees. I think the most, like my door in the hallway can open is 180 degrees, okay? So for my window, my x's, my horizontal axis, I'm just going to go to -1 so I can actually see the y-axis to 10. And then for my y-axis, though, my vertical axis, I'm going to go from -1 so I can actually see the x-axis up to 180 degrees. Okay, I'm going to graph that. Okay, it's kind of like what we did, sort of, right? But this one's opening way faster, kind of comes to a pause, turns around, and then closes at a kind of a slower rate there. So something more like, maybe like that, right? Where this might be 7 seconds, and this was 0 seconds. All right, so number 3, we're going to make a table of values for D for each second from t equals 0 through t equals 10, and we'll round to the nearest tenth. Okay, so this is going to be numerically now, right, using a table. All right, so we'll go, we'll set our table. We're going to start from 0. Oh, change by 1s, go all the way to 10. So here's my table. So there's 0 degrees at 0 seconds. At 1 second, we're at 100 degrees. At 2 seconds, another 100 degrees. 3 seconds, 75 degrees. 4 seconds is 50. 31.3. 18.8. 10.9. 6.3. 3.5. And I need my glasses. How about 2? Or 2.0 since I said round to the nearest tenth. So at time t equals 1 second, does the door appear to be opening or closing, and how do you tell? So this is really interesting. So from 0 to 1, I can tell that the door is opening because it's getting bigger, right? So the rate of change, like if I were to draw some tangent line here, right, it's going to be increasing the rate. It's a little bit confusing. So what happens between 1 and 2 seconds? Is the door just not even open or closed? Does it just stay the same? Well, that's going to require some further investigation. So how about we go into our table and let's go around 1 second. So how about we do like, we'll start at 0.99, and how about we increase by 0.01? Let's see what that gives us. So that gives me some really specific numbers between or right around 1 second, right? So 0.99 seconds, and I can go up to 1.01 seconds. So I can see that at 0.99 seconds, it's at 99.7 degrees. Then it goes up to 100 degrees. Then right after a second, it's still increasing, right? These are still increasing. So it's still opening. Okay, the degrees are increasing. Let's see, as I keep going, they seem to still be increasing. And you can just, I mean, it's fun to kind of use these to help you explore. So I can see now, right about here. So at 1.44 seconds, look what's happening. So we go from 106.14 to 106.15, stays at 106.15, and then starts getting less and less degrees. So right about 1.44, somewhere between 1.44 and 1.45 seconds, this thing starts, it stops and it turns around. Okay, it starts closing, I should say. So it changes from opening to closing. So it's kind of interesting to see that. Okay, I'm going to go back to where we were, give ourselves a little bit of proof here. I'm going to want to see proof. So is the AP exam. So maybe here I can go a little table. So at 0.99, I'm going to go 9.7 degrees. And then at 1, we already knew that we were at 100 degrees. And then at 1.01 seconds, now we're at 100.3 degrees. So I can conclude just based on this that the door is opening. So before 1 second, the door is less than 100 degrees. And after 1 second, the door is, how about greater than 100 degrees? Right? So I've proven it using this table of values, and then I verbally explained it. All right, number 5. What is the average rate at which the door is moving for the time interval 1 to 1.1? And based on your answer, does the door seem to be opening or closing at this time? Okay, so let's do kind of a similar type of thing. So at time, from time being 1 to time being 1.1. Let's figure out what those degrees are. Well, this is 100 degrees. And then at 1.1, which I don't think is on my table, so I'll just go 1 and then I'll increase by 0.1. It's going to be 102.63. Now, it's asking for the average rate of change. So I'm just going to do change in y over change in x, or the change in d over change in t. Okay, so that's going to give me, let's see, if I subtract these two, I'm going to get 2.63. And if I subtract these, I'm going to get 0.1. Right? And so this is degrees per second. Now, dividing by 0.1, I can quickly just move my decimal on top and bottom. So I really end up with 26.3 degrees per 1 second. I'll just go ahead and write per second. Okay, so if the rate of change is 26.3 degrees, that's positive, right? So it's a positive rate of change. So is it opening or is it closing? Well, it's opening. Since it's a positive rate of change. Okay, so we'll have, this will be part of our answer. That's the average rate of change. And then this is the other part of our answer here. So now, by finding average rates using time intervals 1 to 1.01, 1 to 1.001, and so on. So maybe 1 to 1.0001. Okay, make a conjecture about the instantaneous rate at which the door is moving at time t equals 1. Okay, so this is saying, look, you can use a bunch of average rates of change to help you estimate the instantaneous rate of change by getting as close to an instant as possible, right? So we're going to estimate those rates numerically, and then we're going to find the limit of those average rates as the time interval gets closer and closer and closer to 0. So, right, as we keep adding some zeros in here, so we're going to go from, what is that, thousands to 10,000s to 100,000s if we need to. Let's see what kind of information we get here. So I think I'm going to do this on my note paper. Okay, so I'm going to make a table here, which will be kind of helpful in seen the limit of those average rates of change. Okay, so we're going to start with our time column. Then we'll have our degrees column. And then from there, we'll be able to calculate the average rate. Okay. So we're going to go from 1 second to 1.01. And then we're also going to go from 1 second down to 1.001. And so on. So how about we go 1.0001. Let's see how far that gets us. Okay, so at 1 second, we already knew it was going to be 100 degrees. And at 1.01, we already calculated that. That was 100.3. You know what? I don't know how accurate that is. So let's go back to table set. And let's do, change it by 100th. And we can get it even more accurate by actually clicking on it. So how about we go let's go 4 decimal places. So 3023. I maybe didn't leave myself enough room there. Okay, and then let's do thousandths place. So 0.0306. So 100.30. Oops, 0306. And then do the same thing. So 100 point, let's go 5 decimal places now. 00307. How about that? So to find the average rate of change, we're going to basically be comparing this constantly with this point. Okay, we're trying to see, as we have less change in time, right? So this is like the least amount of change in time. What's the average rate that we're approaching? What's that limit of the average rate? Okay, so really this is the shortest amount of change in time between the 1 second and the 1.0001 seconds. Okay, so let's see. I'll go ahead and I'll show you what I'm doing with the math, right? So we're going to subtract these two. So I'll take the bigger number, subtract 100. And when you do that, I guess I could write it out the first time. So it'll be 100.3023 minus 100 on top. That's for my degrees. And then over the change in time, which is 1.01 minus 1. Okay, so really I get that 0.3023, and that was degrees, over, and then that change in time, that seconds, is really just going to be a 0.01 seconds. So my average rate of change then, if I just move this decimal over 2 places or multiply the bottom by 100, do the same on top, it's 30.23, I'll use a degree symbol, degrees per second. Okay, so we're going to do that now. What about, 1.001 seconds? What's the change in time here and the change in degrees here? Well, really, if I take this and subtract that, I just get the 0.0306 divided by, and that's degrees. I'll put a little degree symbol because I'm out of room. Divided by the change in time, which is really that 0.001 seconds. So, again, in the bottom here, I'd have to multiply by 1,000 to move my decimal all the way to the right. And I'll do the same exact thing here. Move the decimal to the right 3 places. So it looks like I'm getting 30.6 degrees per second. Okay, and then here, let's see. So same exact thing, right? Take the change in these two. So I'm going to have that 0.00307 degrees divided by, and then take the difference from 1 to 1.0001, so that's 0.0001 seconds. Okay, so it looks like here I'd have to multiply by 10,000, right? Top and bottom, or move the decimal over 4 places. So when I do that, 1, 2, 3, 4, I get a 30.7 per second. Okay, so it looks like we're getting a little bit closer. We did quite a bit of jump here. Maybe let's go one more just for fun. I'll give myself a little bit more room here. So I'll go 0.12341. That's interesting. What's going on here? Oh, that's weird that that looks like that. Okay, so it's 1.000, so 4 zeros, 1, and I'm getting 100 point, now 1, 2, 3, looks like pretty much the exact same thing, 307. So I think from there, I'm going to actually put my average rate of change. Look at that. So this is going to be 0.000307, and then I'm going to move the decimal over 1, 2, 3, 4, 5 places. 1, 2, 3, 4, 5 places. I'm going to get right back to 30.7. So we basically approach the limit of the average rates is going to be 30.7 degrees per second. So there it is right there. Right, and we just double check that by going one further. Okay, so that's what it means to find the average rates of change, right? And then to find that limit, right? So we're estimating the derivative. We're estimating numerically, right? We used a table. And then by finding the limit of the average rates of change as the time interval gets closer to 0. I think actually we should take that and out. That doesn't really make any sense. So estimating the rate of change numerically by finding the limit of the average rates of change as the time interval gets closer to 0. And we are done for today.